All right, we are now in week like 10. We'll be 2/3 of the way through after this week. So that means it's time to focus hard because the semester is going to wind down fast. Feels really quick. All right, we're going to do one more of these telescoping series, then we're going to have some really interesting examples today that are kind of start to get very abstract. But before we get to those abstract examples, very tangible telescoping series. So this may not look like the telescoping series that we've done prior. Let's see, let me just shrink that a little bit. So, a lot of the telescoping series we see look like a difference of rational functions. This one looks a little different down here, but we'll see what it looks like. Whenever we're dealing with a telescoping series, we need to find S sub n. So once again, telescoping will be the only other type of series that we can find S sub n for. Any series that you have, if you can find S sub n, you're golden, because then you can take the limit of S sub n and figure out if S is finite or infinite. But there's only two types of series that we are going to see that you can find S sub n. Telescoping, geometric. Only two. All right, so here we plug in our 1 first, and we're going to get the square root of 2 minus the square root of 1. So that's the first term. The second term, we're going to plug in k equals 2, and we will have this. The third term, and yes, you can simplify these square roots, but let's not. We can keep track of what's happening if we don't more easily. So we always need the first 3 terms, and then we are going to need the last 2. So this series is nice because it has a counter that starts at 1. So that means that the counter is keeping track, the index is keeping track of the term number. So if we want to get out to the nth term, we just have to go through the k values 1 through n. So to get to the a sub n minus 1, the n minus first term, we're going to plug in a sub n minus 1 in for k. So actually, this should just be n minus 1. N minus 1 here. The index value is n minus 1. This coefficient will be called a sub n minus 1. So let's plug in n minus 1 in there. So we'll get the square root of n minus the square root of n minus 1. And then for the very last term in S sub n, we are going to have square root of n plus 1 minus square root of n. So that is S sub n. Once we have S sub n, then we can take its limit to figure out if there's an S or not. But we want to simplify S sub n and get it down into a closed form here. So we're going to cancel out whatever we can. Let's see. So as we're moving left to right, first part with second of subsequent. Moving left to right, first part is going to cancel with the second part of the next. So then this one right here, this is a first part. This first part will cancel with the second part of the next term that's in the dots here. And similarly, when we go right to left, same thing. We're canceling these sort of, the outer, if you think of the FOIL technique that you used to use. We're canceling the outers. So then this is going to be an outer with something that's also in here in the muck. And for this particular problem, we see that we are going to have two terms that don't cancel, that don't go away. So there are only 2 terms. So that tells us that S sub n is -1 plus the square root of n plus 1. So this tells us the sum of the first n terms for whatever n you want to plug in, positive integer. So it tells us the sum of the first 2 terms. Let's just note that if we wanted the sum of the first 2 terms, we'd be adding up these 2. Right? These are the first 2 terms. We see that square root of 2's cancel, so we should end up with square root of 3 minus 1. Sure enough, if we plug in 2 right there, we get square root of 3 minus 1. So it will tell us the sum of the first n terms. And now if we want to decide whether this infinite series converges or not, we take the limit of s sub n as n goes to infinity. And what's that going to be? Infinity. So this tells us then that the series diverges. So therefore, we have a divergent series.
How does it diverge, though?
Goes to infinity. So the sum gets progressively larger.
So it diverges monotonically, according to Pearson?
Yeah. Yep. Yeah. It will diverge by getting bigger, 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 bigger. It's going to be like inflating a balloon. There's no oscillations. Big balloon, and then it's going to pop. Okay, so let's start looking. Any questions on telescoping? So telescoping and geometric, those are the only two that we have of this technique where we can find S sub n. So let's look at some of these interesting problems that come up in this with this topic. So back in the day, before calculus was invented, it was a big deal to try to find the area of regions that weren't geometric, regions that you couldn't find formulas for really naturally. So finding the area of a parabola, super hard. And so what Archimedes did to find the area of this parabola exactly was to create a geometric series that was convergent. So if we take this parabolic shape here and we put this triangle here called a sub 1, and then what we're going to do is bisect down here. We want to bisect these two intervals, this right-hand interval, bisect this left-hand interval, go up, create these two triangles. So step 1, we've got the pink area. Now we've got two extra triangles, A2, so we have two A2s. And then we're going to do that same thing again. We're going to bisect again. So we're going to bisect here, 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 go up to the curve. I can't draw it in that tight little space, but we're going to end up having a whole bunch of triangles. Let's go with red and see if we can possibly make it work. So if we come up here, we've got that red dot, and then we're going to create this triangle in there. And similarly, right here, we're going to create this triangle. It's going to be very messy looking. But how many triangles will we have at that stage then? 4. There's 2 right triangles on each side. 2 plus 2 is 4. So we're going to have 4. These will be called A3. And it will turn out that each step of the way, you're going to double the number of triangles. So we went from 1 triangle to 2 to 4 to 8. Moreover, you can show, it's not trivial, but you can show that these two A sub 3's are going to have the same area. May not look like it, but you can prove that those two have the same area, which is why this formula will hold. You can show all the way down that each of these, the 8 A4 triangles will each have the same area. So you get that. The hard thing, the crux of the proof is this. You can show that at each stage, the next triangle is an eighth as big as the prior triangle. So the area of a sub 2 is an eighth the area of a sub 1. A sub 3 is an eighth the area of a sub 2, etc. So we're going to replace the a sub 2 with a sub 1 over 8. And then we're going to replace the a sub 3 with 1/8 of that. And then we're going to replace the a sub 4 with 1/8 of that, etc. And it creates a geometric series. So this tells us the exact area of that parabolic region. We factor out the a sub 1. There's our geometric series. And this geometric series, we see that we've got the r value of 1/4, and the first term of 1. So it's just a 1 multiplied out here. A sub 1 is out in front, factored out, and then we use our formula. A divided by 1 minus r. There's A, actually, right there. There's A. A divided by 1 minus r. So this gives us the area of a parabolic region that did not involve calculus. So for example, let's take a look at 1 minus x squared, simple parabola. If we inscribe this triangle right here, the area of this triangle is half the base times the height, so the area of that triangle is 1. And then if we plug in 1 right here, for a sub 1, we get that the area of the parabola is 4/3. All we did was plug in the area, first triangle, and we get the total area. If we use calculus, we just integrate that, and we get 4/3. So geometric series, the key here is that we created a geometric series that was able to do what we wanted it to do, to be able to find the area of an obscure region. And we're going to see the geometric series pop up all over the place.
Jim?
Yeah?
Is it important to have that second part? Because on the printed notes, it's not there.
No, it's not that important. Yeah, you're not going to be tested on it. This is more of just an interesting side note for a minute. I'm not going to ask you to. So they call this the method of exhaustion. You're kind of exhausting all of the area by slowly adding a little bit more, a little bit more, a little bit more. So you're kind of exhausting the region.
Kind of like a Riemann sum, but not.
Yeah, I mean it's very it's very similar to a Riemann sum. All right, so let's take a look at the properties of series. And there's the intuitive properties that we've kind of talked about already. If you've got a series that converges and you multiply by a constant, that constant can be factored in or out or pushed in. It doesn't matter. You're going to end up getting a constant times whatever the series converges to. So super intuitive, same as limits, same as derivatives, same as integrals. Constants can move in and out of the symbol. Same for all those types of situations. If we have a series that diverges, there is no constant that you can multiply it by to make the series converge. So if you have a divergent series, you can't make it convergent by multiplying by a number. It's still going to diverge. So you can't offset divergence. If you have two series that converge, so these converge to A and B, then the sum or the difference will converge to the sum or the difference. Again, same as limits, same as derivatives, same as integrals. You can distribute that summation symbol if you're dealing with a convergent series. Similarly, if you have a series that diverges and a series that converges, then it doesn't matter, adding or subtracting diverges. You cannot take a divergent series and a convergent series and make that combination converge. So no matter what, if one of the series diverges, you can't add to it a convergent series and make it converge. Right? If it diverges, it goes off to infinity. And if you add a convergent series, means that it's a finite number, right? Its value is finite. Can't add that to divergent to make a new convergent series. So if one diverges, the sum or difference diverges. And then this one kind of illustrates the property that we talked about last week. Here we have an infinite series. Here we have the tail of that same infinite series. This series starts further down in the index chain. All right, the index starts at 1 here. The index starts later there. They do the same thing. They either converge or diverge. They have to do the same thing. So that's that whole principle that if you have an infinite series that converges, chopping off the first 1,000 terms doesn't change anything. Still converges. What does change is the value that the series converges to. Right? If you chop off the first 100 terms, that's going to create a series that converges still, but it's going to converge to a different number. When you look at a convergent series, the front, the head of the series, the leading terms, those are more impactful on what the series converges to. The tail is equal to 0, essentially, right? It's equal to something really close to 0. So the value of an infinite series is dominated by the leading terms. The tail of the series usually is very close to 0. So these two, the whole series and the tail of the series, both converge, but they're going to converge to different numbers if you chop off some of the terms. They'll still converge, just to a different number. So that's kind of summarized in this paragraph here. So yeah, the tail of the series is the end, blah, blah, blah. It says what I just said. All right, so let's take a look at our first really bizarre thing. Koch snowflake. The Koch snowflake is our first example of a fractal. And it's found by creating this shape over here to the right. We've got four stages of the Koch snowflake. You build it by chopping out the middle third of each segment and then taking that, so these distances are the same here. So this distance here, that's going to match this and this. So that's an equilateral triangle right there. And so you chop out a third, each of the sides, create this shape, and then again, rinse and repeat. Cut out the middle third, create another equilateral triangle. So at each stage of the game, you're taking, so here we had one side, now we're going to have four, or I should call it an edge. We have one edge, now we're going to have four edges. But each edge length will be different in length now. This edge has length 1, this edge, each edge will be 1/3 because we chopped out the middle third. So this table sort of walks you through the stages of creating the number of edges or segments per side, the length of each segment, and then the perimeter, which is S times L, and we multiply by 3 because we've got 3 sides. And this is going to end up being, whoops, not that one. The next one down is going to end up being the perimeter. So here's our perimeter. Come down here, perimeter, infinite. That's a geometric sequence that we're taking the limit of. Geometric sequence with an R value of 4/3. Bigger than 1, multiplied by itself, goes to infinity. 4/3 times 4/3 times 4/3. So the perimeter is going to be infinite. The area we're going to compute by looking at, okay, there's the first triangle. And then we're going to start adding up all of these extra little triangles that are going into the process. And that's what happens down here. So number of extra triangles. Here's the generalization. The extra triangle area is right there. You multiply those together. Excuse me. You add those. Right, we're going to add the area of the first triangle, which is right here. And then we're going to add all the other ones, which are right there. Long story short, if you do the math here and look at each of the components, you end up with a geometric series down here. And this geometric series has a common ratio of 4/9, which is less than 1. So you have convergence. We plug it into our formula for a geometric series, and that is the area of the Koch snowflake if you start out with a 1 by 1 by 1.
Is this another thing that's just like, this is how we apply it in real life, or do we have to know this?
It depends. So on the exam, there will be an extra credit question. This is the only test in the course that's going to have an extra credit question. This is one of the choices. It will either be Koch snowflake or Riemann zeta, which we're going to talk about later. So if this is the extra credit question, you've got to regurgitate and show that the perimeter is infinite and the area is finite. So if you dig in and figure it out and then can regurgitate it on the test, you'll get 5 points. Dan?
So for the previous exams, or we can use a study for the exam, will one have an extra credit Koch and the other will have an extra credit Riemann zeta?
Yeah.
Okay.
Mm-hmm. Yep. Yep. Yeah, so it'll be, so that's, if you want to dig in and figure out the math here, it's worth points. If
Is
it's,
your
if
extra,
it's the
is your
credit
extra
one.
credit to solve the Riemann hypothesis or something?
No! We are not solving the Riemann. Not the Riemann hypothesis. Not today.
Before you
Zeta
move
of
on,
negative
Yeah.
1 is 9 to 12.
Perimeter calculation, because it didn't print off, it's just the same as,
So the perimeter calculation,
is the.
if you look right here, that's the perimeter. So the perimeter, we have 3 sides. There's the side length right there, and that's the segments
Okay.
per side. So that's that formula. So if you take the limit of this as n goes to infinity,
I think it's,
that goes to infinity.
Okay.
So that's the perimeter. Area calculation is down here. It's going to be this. It's going to be this, you know, all the triangles plus the extra triangle area. So it's those multiplied together plus the original triangle.
okay.
All right, so let's go into our first test beyond the special series. So we have looked at geometric series, which they're going to classify as a special series, because they call it special primarily because we can find the sum of the series. Telescoping is also special. We can find the sum of the series. Now we're going to get to some just sort of general ideas behind convergence and divergence. Yes, it converges. I don't know what it converges to, kind of thing. So if it's not telescoping or geometric, all we can do is say, yes, it converges, or no, it doesn't, it diverges. So we get much more general, a little more abstract, not as concrete. So the first thing is the divergence test. We know that for a series to converge, the sequence of terms must go to 0. Everyone agree? Right? We have to be, when we get out to the tail, in the visualization in your mind for a convergent series, you should be thinking like the improper integral things. You should be thinking about a ski slope that goes down to the x-axis really fast. Right? So the terms have to be going to 0. These term values, they have to be going to 0. If they don't go to 0, if that limit's not 0, then we have divergence automatically. Everyone crystal clear on that? If the limit is, say, 1/5, that means in the tail of the series, it's like 1/5 plus 1/5 plus 1/5 plus 1/5. That diverges. If you add a fifth to itself an infinite number of times, that's infinite. Right? If you add a millionth to itself an infinite number of times, that's divergent. That's going to be infinite. So if the limit of a sub n is not 0, you know automatically the following. You can conclude this. If the limit is not 0, then the series must diverge. But we have to be careful. There's a little gray area. This says if the series converges, then the limit is 0. It does not say if the limit is 0, the series converges. Right? Because we know already the harmonic series. The harmonic series, this diverges. We know that this diverges. So we have to remember that the converse of this is false. This just says if the series converges, the terms must go to 0. So that's necessary, but it's not sufficient. Just because the limit is 0 doesn't mean it converges. But if it does converge, we do know that the limit is 0 of the terms. Okay, all right, so here we go. So first off, the divergence test, it can't be used to show convergence. The divergence test is a quick little, hey, the limit of a sub n is not 0, the series diverges. If the limit of a sub n is 0, we have to do more work, right? Because of the gray area.
So it's just a quick little check.
Yeah.
Divergence.
So, for example, well, we'll get to an example, but yes, yeah, it's a quick little test. And if that limit of a sub n is not 0, it's super fast. You're done. You know, like if you just look at a simple series like this. This is geometric. Does that series diverge or converge? Well, if we take the limit of 2 to the k as k goes to infinity, that's infinity. Therefore, this series must diverge. Right? So if the limit of a sub k is not 0, you know instantly that it diverges.
So it's the answer to the divergence test is always either divergence or
Or inconclusive, right? So if the limit is 0, then it's inconclusive. So the divergence test either says, yes, it diverges because the limit is not 0, but if the limit is 0, then the test is inconclusive. We don't know, does the series converge or diverge? It could do either. It's kind of like an indeterminate form. We don't know. Okay, so let's talk a little bit about this idea of converse and contrapositive, because right here I use the word converse. So this says if the series a sub k converges, then the limit must be 0. The converse of that is going this direction. The converse would be limit of a sub k is 0, therefore the series converges. So that's false. The converse is false here. And this is kind of a statement that can get us to think about these ideas of converse and contrapositive. So contrapositive is this. So first off, let's read our thing. Here's our sentence. So our sentence says, if I live in Paris, then I live in France. We're talking, you know the Paris we're talking about, the one with the big, that thing, the tower. So if I live in Paris, I live in France. The contrapositive of that is always true. So the contrapositive is an equivalent way to prove something. So if you were to try to prove something, you can either use the direct method, or you could go to the contrapositive. So if you find that the contrapositive is an easier statement to verify, then that will verify the original statement. So contrapositive, I don't live in France, therefore I don't live in Paris. That's a contrapositive. So it's negating both of these. So I don't live in France, so therefore I can't live in Paris. The Paris, not Paris, the other Parises. The converse, I live in France, so I live in Paris, obviously that's false. You can live, anywhere except Paris, and you still live in France. So those are the two ideas between converse and contrapositive that come up with this type of topic. Any questions on those two words, converse, contrapositive? When you get into higher math classes or logic or some other courses, if this was supposed to be, you're going to see the word if and only if, IFF. That's going to mean that both directions imply each other. So here, A implies B, but B does not imply A. If we wanted it to do both directions, then it's called an if and only if. Then this being true means this is true, and this being true means that is true. So you'll see that kind of logic later. We don't need it here, though. We don't need it here. Okay. So let's take a look at the divergence test. So either the divergence test will conclude divergence, or it will be inconclusive, one or the other. So to use the divergence test, we say the limit of a sub k as k goes to infinity. So we have that. And what is that limit? How many?
Indeterminate form.
0?
L'Hopital's law.
There are 3 ways we can do this. First way, so certainly I heard Austin say it's an indeterminate form. When we first look at this, yes, it's indeterminate, right? We have infinity over infinity. So you could use L'Hopital's rule. It's indeterminate. You could use L'Hopital. You could use a concept that, let me write it here. If you have a polynomial, the leading term dominates. So you can just chop off all the garbage that's smaller than it. It's insignificant. The leading term dominates. So if you just grab the leading term, that's okay. For polynomials that go to infinity, the smaller powers don't matter. The only one that matters is that. So you could do it that way and just say, hey, I'm just going to look at the dominant power of each of these polynomials, And that simplifies to 1, and the limit of a constant is itself. So that's one way to do it. You could divide everything by the highest power of k. If you divide everything by the highest power of k, you could go this way and say, oh, it's the limit of 1 over 1 plus 1 over k cubed. And 1 over k cubed goes to 0, so this also goes to 1. So we do it that way. If you use L'Hopital's rule, you would get 3k squared over the derivative here, which is 3k squared. 3k squared over 3k squared is 1, and you're back to this. So 3 ways that you could do that limit. This limit is not equal to 0. Therefore, this series diverges. Has to diverge. Has to diverge if the limit is not 0. Okay, here's another one. So another one here, we take the limit of a sub k. So the limit of k over natural log k. And once again, we would say, oh gosh, both numerator and denominator go to infinity. Therefore, we need to do something. We need to use some analytic tool to evaluate that limit. Here, L'Hopital's is the only tool that makes sense. We can't divide by the highest power of k and make that make any sense. If you have a rational function, that does work. Here, that does not. So we take the derivative. So we're using L'Hopital's rule right here. Derivative of the numerator is 1. The derivative of the denominator is 1 over k. So we're going to get a limit of k as k goes to infinity. That's infinity. This is not equal to 0. Therefore, diverge. Another one. So what's this one going to be? 0? Yeah. So we have polynomial over exponential. So we know that by growth rates, this limit's going to be 0. But this is one that we can take the limit of. We don't have to use growth rates, so we need to show it. So this is indeterminate. We are going to use L'Hopital's rule, so use L'Hopital. And what is the derivative of the numerator? 2k. Derivative denominator? Derivative of an exponential? Start with itself. Multiplied by? Derivative of the exponent, which is 1, multiplied by? Log 2. Log of the base. So if you have an exponential other than e, you always have that little extra factor, natural log of whatever the base is. Okay, so now we have that. Doesn't that still, is that still indeterminate?
Yeah.
Yep, so we're going to use L'Hopital again. Still infinity over infinity. So the derivative of the numerator is what? 2. Derivative of the denominator is?
Something with k in it.
Really?
Genius.
2k times
Exactly, which
natural
means
log
that
2
you have to,
times
you don't have to
natural
do
log
any
2.
more.
What Daniel said is exactly right. What Harrison said is marginally right.
Marginally.
So remember, natural log of 2 is just a constant. So we're just differentiating 2 to the k again. The derivative of 2 to the k, which we already did, is 2 to the k ln 2. So we have ln 2 times ln 2 times 2 to the k. So we have ln 2 quantity squared times 2 to the k. Now this is not indeterminate. What's that limit? Which is? Zero. So therefore, inconclusive. So that limit is 0, so inconclusive. This series might converge or it might diverge. We have to do further math.
What's the exclamation point?
Factorial. That's what we did on Thursday.
Out of curiosity, why do we not go with factorials until like count 2? Because I don't remember in algebra.
They're in stats. So if you ever take stats, you do them. So just as a reminder, 6 factorial. Yeah, we just do repeated multiplication all the way down until we get to 1. So yeah, we do them in Calc 2 just because you don't really need them in Calc 1. The functions that have factorials are just very hard to analyze, so they don't show up in Calc 1.
How does the factorial function work when you put a decimal in?
So, great question. There is, if you want to use L'Hopital's rule, you have to take a derivative, right? In order to take a derivative, you have to have a continuous differentiable function, right? When you're thinking about the factorial function is discrete. But there is a function called the gamma function. And the gamma function is the factorial function's extension to all real numbers, so including all those decimals. So if you want to know 3.2 factorial, you go to the gamma function and you look up gamma of 3.2. And that will give you, you know.
Because I plugged in x factorial into Desmos and it still gave me a graph. So what was
Yes,
the graph?
gamma function. Yep.
So discrete means only like positive integers?
Yep.
Positive and negative integers.
Yep. Yep. So that's how the factorial function is extended. Yeah, there's gamma.
Oh, yeah, gamma.
There's gamma
That's
function.
gamma?
That's the gamma function. The gamma function is how you can do those things.
That's weird.
You know, it's kind Gage,
So what's like 1 half factorial?
you'd have to look up the gamma function. I don't know what it is off the top of my head. It's some irrational number.
So how did they make that up?
How do they build the gamma function?
Yeah.
That is a good question. I don't know how it was originally created.
What that is?
Is
I don't know.
it based off radiation?
Is it
Like them experimenting?
No, I don't think
Different kind of gamma.
so. Yeah, I think it's different than a gamma ray. I don't know why they called it the gamma
Well,
function.
actually, no, I think that's never.
We'll have to look it up.
What is the gamma function?
So, x factorial. All right, so once again, we're going to take the limit. So we're going to take the limit as k goes to infinity. And here we don't know, this is indeterminate, we don't know how to take the derivative of the factorial function. The gamma function is a totally nasty looking thing. You don't even want to look at it until you have to.
Doesn't it have like double-tailed improper integrals?
There's all sorts of things in it. And so we can't do this. So here what we are going to do is use growth rates. Here we have to use growth rates because we don't know how to differentiate k factorial. So this limit is going to be 0 by growth rates. So we know by growth rates, so that chart that we had on the tape on the board last Thursday, that's all we can do in a case like this.
So if we don't have, like, let's say it is like the one above, where we are able to use both growth rates and solve it, we have to solve it?
Yes. Yeah, if you can evaluate the limit not using growth rates, using an analytic technique, then you have to, yeah.
You can use
It's
Harrison's
called
method
math.
for
It's
it.
like doing it the hard way when you like know the answer already.
Yeah, I've heard that from you a lot.
Why can't
Say that again?
Why can't we use the growth rates if we can solve it?
Because we use growth rates only when we're not able to actually do the computation. Growth rates is, you know, the hand waving thing, where it's like, I'm pretty sure, but it's not a guarantee because you didn't prove it mathematically. If you can do it mathematically, you do it, but if you can't, we're just going to use growth rates until you can do it mathematically in a few semesters. when you're in Calc 5.
So,
Oh my gosh, I don't even want
so using growth rates isn't a
Ew.
guarantee then.
What's that?
So using growth rates isn't a guarantee.
It is a guarantee, but it's not,
That's
it's not
nasty.
mathematical proof.
Okay.
It's kind of, it's just,
That makes, okay.
it is true, growth rates is true, it's just not, it's not, you know, it's not as, we always want to be as precise as we can.
Okay. Yeah, that makes sense.
Like the method.
My method is precise.
Oh my
No
gosh.
idea.
Here we go again.
That's still precise.
Okay, so we've already seen this. You have to have this series in your back pocket because it's a really good thresholdy type thing. We know that the harmonic series is going to diverge. And we didn't actually prove it, though. We looked at the improper integral of 1 over x and showed that that diverged. That's a little different than the series, but they are related. So let's go ahead and prove that the harmonic series diverges. So in order to prove the harmonic series diverges, first we're going to look at S sub n, and then we're going to see what we can gather from S sub n. So what I'm showing you here is a visualization for S sub n. So if we look at the terms of the series are these points right here. And these rectangles are just giving us a visualization for S sub n. Right? So the series is 1 plus a half plus a third plus a fourth. We can visualize those values as areas of rectangles that have a width of 1. Right? This height is the same as this area.
That very last point, would we not include that since we're only including the left part of the triangles? Or the rectangle.
I mean, if we're only looking at the rectangles, I'm just looking at all these points create these rectangles. Right? This is 1 over n right here. This has area 1 over n. So that's a visualization of the nth rectangle,
Okay.
which is the nth term in the series. Okay, so if we look at, so these rectangles have more area than the area beneath the curve, right? So the partial sum is the sum of these green rectangles. That's more than if we integrate from 1 to n plus 1.
That would be a left Riemann sum, right?
That's a left, yeah, whatever you guys did in Calc 1. I don't know what you call it. We're using the left endpoint right there. So, but for an integral, though, we're integrating from 1 over to n plus 1. Right? Everybody see that the partial sum is bigger than that integral?
If S of n is the green boxes, why doesn't it go 1 but then 3 halves if it's like adding?
That's the S sub n sequence.
Oh, okay.
So these are the A sub n's. This is A sub 1, this is A sub 2, this is A sub 3, that's A sub 4. S sub 1 is 1, S sub 2 is going to be 1.5. S sub 3 is going to be the sum of those three. So that sequence is the sum of them. And but we can visualize that with this area, right? The area of the green boxes gives us S sub n. That gives us a visual for S sub n. And clearly that is bigger than that integral. So if we look at, if we look at this integral, we know that S sub n is bigger than it. So let's look at this integral. We're going to go from 1 to n plus 1 of 1 over x. That integrates to the natural log of the upper limit minus the lower limit. Log property, we know that that's 0. So this integral, that definite integral, has this value, and what's the limit of this as n goes to infinity? Right? So this goes to infinity as n goes to infinity. And S sub n is bigger than it. So if S sub n is bigger than it, then S sub n also goes to infinity. Right? So if S sub n is bigger than this, and this goes to infinity, then S sub n also goes to infinity, so the series must diverge. So that is the proof that the harmonic series actually diverges.
Even though its improper integral doesn't.
Yes, it does,
Oh, my bad. Never mind.
right? If the power on x in the denominator is bigger than 1, then you have convergence. Right? So when we did the improper integral, the integral of 1 over x from 1 to infinity, this is infinite. The power has to be bigger than 1 down here. This will converge if you go from 1 to infinity, as long as that power is bigger than 1. But if that power is equal to 1, you have divergence.
So is that S of n?
That's sub n.
S of n.
Sub.
Greater than the integral of, so is that a formula?
Mhm.
Or is that the integral test, or is that,
Not the integral test, not yet.
what is that called?
This is called an inequality.
Okay,
That's it.
just an inequality.
We're choosing this inequality to prove this specific instance.
So
It's going to lead to the integral test shortly, though.
does it only prove for harmonic series?
Yes, this technique is we're just proving for harmonic. But we are going to create a more general test that would apply to the harmonic.
I see.
Wouldn't each box, like the next numbers, like 1, 1/2 would be the sequence, but then adding them up would be the series?
Correct.
Okay.
And adding them up gives you area,
Yeah.
right? Adding them up gives us area. So now we get to the integral test. So obviously you've all sort of noticed that, hey, there seems to be a connection between series and improper integrals. So here we go. Here is the divergence test is a test, but this is, so this is our second test. This is our first sort of, divergence test feels more like doesn't feel like a bona fide test. You're just taking the limit of a sub k, but it is a test. So here's our second test. Here we go. So first off, f is continuous, positive, and decreasing, i.e. quadrant 1 decreasing function, this ski slope. Positive valued, continuous, and decreasing. So that is our ski slope. And a sub k is coming from the function. The function is building the sequence terms. So both the series and the improper integral do the same thing. They both converge or they both diverge, one or the other. So that is the integral test. It says that your infinite series and your corresponding improper integral do the same thing. Here is the justification for that. So here we have our definite integral. Remember that when we did these improper integrals, didn't we picked a stopping point and we created a definite integral, and then we took the limit of that result. That's what we're going to do here. So here is our definite integral. We'll stop at n. Now let's look at these two pictures. So here, a sub 2, a sub 3, a sub 4, those are lined up over here. This beige and that green there, those a sub 2s have this, those are the exact same rectangles. Okay? Same rectangles. So we are going to look at these rectangles that are underneath the curve from 1 to n. Right? So all of those in there, if we add up these rectangles from this x value of 1 to this x value of n, we add those all up, there's actually how many rectangles there? N minus 1, right? Because we started counting at 2. So right there we have n minus 1 rectangles. Those rectangles match these. But this summation here, we're going to add these rectangles, a sub 2, a sub 3, all the way up. Do you agree that that's less than the integral, the area beneath the curve from 1 to n? Right, we can see it. Those rectangles are all below, so the area is less than that integral. Now let's look at a different perspective. So we left off this rectangle that was over here, right? The one that's here. We ditched that one. Now let's look at that rectangle and look with the taller rectangles here. And if we look at the green rectangles here, if we integrate again, 1 to n, that's just the area under the curve. We're dealing with the same curve. Now if we look at the green rectangles, we're adding a sub 1 up to, we still have n minus 1 rectangles, but this area is an overestimate to the area beneath the curve. So the integral has to be in between those two. All right?
Can you scroll up a bit?
So does everybody see the visualization? You know, whenever we build these rectangles, there's always two perspectives. So you could draw your rectangle to the left, or you could draw your rectangle to the right. So here we've taken the number of the endpoints here, and we've drawn the rectangles over here. We're drawing them to the left of the points of intersection with the curve. So we have our points of intersection with the curve, and we're drawing left rectangles. Here we take our points on the curve, and we're drawing right rectangles. So we take that point, we take the rectangles to the right, take that point, take the rectangle to the left.
And this is because of the one on the left is n, and the one on the right is n minus 1.
Yeah, so they both have n minus 1 rectangles.
Yes.
They both have n minus 1 rectangles. It's just that this one we're starting with the rectangle of that height. Here we're going to start with the rectangle that's taller. But here we're going to end sooner than we end over here.
I'm just asking that because on the top of the...
Here?
No, on the very top of that, yeah. See how that one says n minus 1 on the top, the other one says n?
But this one starts at 2.
Yeah, but if it started at 1, would it matter? Because it would just make...
Well, then it would change the integral. We want the integral to go from 1 to n.
Yes.
So when we're looking at the interval from 1 to n, we can either use rectangles that were created from the right or from the left. So if we are counting these rectangles, we're starting at a sub 2, so there's still n minus 1 rectangles.
Oh, okay, I see what you're saying.
So there's n minus 1 rectangles in both cases.
When would we use the divergence test, and when would we use it?
We always think about the divergence test first, because you can look at a sub k, and if that limit's not 0, you know you're done. And so if you look at the divergence test and you get a limit of 0, then you go to this. Yeah, make sense? Ari?
So the inverse tangent of x as x approaches is going to be this pi halves, right?
Yep.
So would you say then in that direction the value is always increasing though?
Yes.
So something can increase indefinitely but retain the same value?
Yeah, so you're just talking about a limit at infinity.
Right.
So arctan has a limit at infinity. So the limit of that sequence converges. But that's not a sum. That's not a series.
Right.
The limit of the series diverges.
The limit of the series would diverge, because it would be like adding pi over 2 plus pi over 2 plus pi over 2 repeatedly. So the sequence, when you're looking at that arctangent function here, so this sequence of terms is going to converge to pi over 2. But if you started adding all of these together, those rectangles that you could visualize would, add to infinity.
Right.
Right?
So for an increasing function, if you just flip those around.
If a function is increasing, the series is diverging.
Oh, yeah.
We always are going to have this assumption: continuous, positive, and decreasing. So that's going to be our baseline, is that we're always dealing with the ski slope.
So
If you have arctan that's increasing, any function that's increasing that builds sequence values will have a series that diverges. So the series only can converge if it's a ski slope.
So in that case, say the divergence test was inclusive. You went to the integral test, but the function is not either continuous, positive, or decreasing.
Then you go to a different test.
Okay.
Yep.
So this is like a branch of a test.
Yeah, we're going to have a whole bunch of, if the function is not integrable for whatever reason, then you have to go to a different test. Yeah. Okay, so let's try this test. So here is our infinite series. We are going to create a function that is going to generate those values. So all we do is this. We just replace the k with an x. So here is the function that we're going to look at. That is going to be positive valued, decreasing, continuous, all the things. It's going to look like a ski slope if you graph it, right? The limit is 0. Right? Denominator gets bigger and bigger, fractions get smaller and smaller, so it's a ski slope. So all we have to do is take a look at this integral. So if we integrate from 1 to infinity that function, then this integral and that series do the same thing. Both will converge or both will diverge. So the first word that we always write down when we're dealing with an improper integral?
Limit.
Limit. First thing we do, write down limit. This limit will be as whatever b goes to infinity, whatever your letter of choice is.
So b, not n in this case?
Whatever you want, doesn't matter. It's your choice. So this is going to be popped up into the numerator, dx. And we're going to go from 1 to whatever letter you want. I'll go to b, since that's how we did our improper integrals. So now we just have to integrate that. We use the power rule and reverse chain rule, all that stuff. So we're going to have 2x plus 4. If we add 1 to the exponent, divide by the new exponent means we're going to divide by -1. What else do we have to divide by? 2. So reverse chain rule. Everyone agree with that? So add 1 to the exponent, divide by the new exponent, take the derivative of the base, divide by the derivative of the base also. So we are going to have a limit of -1/2. I'm going to pull that all the way out to the front. -1/2. And let's put this like that. And this should have a 1 to b still. So this is 1 to b. Then we just evaluate at b, evaluate at 1, and then take the limit. So let's do that. Where's my splitter? Okay, so we have -1/2, limit as b goes to infinity of 1 over 2b plus 4 minus 1 over 6. And what is that limit?
-1/6.
So that limit is -1 over 6. So we get a total of 1/12. Everyone clear that this part goes to 0?
You forgot the minus sign on the 1/12. Just kidding.
Why do we have to have a 1/12 as an answer?
It's an awesome answer.
1/12.
Okay, so let me just finish this off.
Okay.
So this is not equal, this is, it doesn't matter that this is not 0. This is a, let me do it this way. This is a positive real number, which means the integral converges. So this epsilon is used in set notation to mean is an element of the positive reals, which means it converges. Right? So an improper integral, as long as you get a number, it converges, positive number, because the function is positive. So that converges, and so that tells us that the series also converges. So we could just say both converge. Probably easier. So because that's a positive real, that tells us that the improper integral converges, and if the improper integral converges, then the series converges.
So the integral test is basically, all it is transforming it into an integral and then running it through, and then you check if it's a positive real number.
Yep.
And if it's a negative real number, is that one?
It can't be negative because we already assume the function's positive and decreasing.
Okay. But there's another case where it's divergent, correct?
It would be divergent if this is infinity.
If that's infinity. All
So
right.
this is either going to be infinity or a real number,
Okay.
a positive real.
And you said when we're dealing with these, we can either only say it converges or diverges. We can't say.
Great point. So this integral converges to 1/12. That does not mean the series converges to 1/12.
Okay.
So this 1/12 is the area beneath the curve. and it may or may not be the sum of the series. So this all we can do here is conclude that the series does converge, but it doesn't tell us what it converges to. Yeah, good question.
So we could also write that the series is an element of the real positive reals.
Yeah. All right, let's go ahead and take our 10-minute break, and then we'll get into some funky natural logs hanging out in the denominator. Basement dwelling log functions. We did some of those with improper integrals. 1 over x ln x, 1 over x ln x quantity squared.
Imagine doing an improper integral, only you have to do L'Hopital's for the limit.
There we go. L'Hopital's. All right, let's find the pause button.
Yeah.
All right, so let's do, so if you remember, when we did improper integration, we know that 1 over x diverged, and then we said, okay, well, let's try to increase the denominator faster, but not too fast. We know 1 over x squared converges. And then we did 1 over x ln x, and that also diverged. And so what they're going to do here with series is very similar. They want to start bumping up the power on natural log and see how many it takes for the denominator to grow fast enough that we get convergence. So let's try this. So we're going to look at the integral here from 2 to infinity of, and all we're going to do is change all of the k's to x's. And so now we have natural log of x quantity squared. Let's just make that a dx up there. So that is our corresponding improper integral. So now we need to evaluate that. So once again, improper integral, first thing we do is write down limit as b goes to infinity. And we create a definite integral. And then we evaluate this definite integral and take the limit. So, what technique of integration? Substitution. What are we going to let u equal? Say again?
ln x.
ln x, yep.
Are we going from k to x and x is a dummy variable? Is that what's going on?
When we are dealing with a series, we have discrete values, so we usually use a k or an n. When we go to an improper integral, we use x's because we have a continuous function.
Okay. What do you mean by discrete?
Discrete means dots. Dots.
So discrete math is dot math?
Discrete math is dot math.
Is that true?
I mean, discrete math is studying things that are not continuous functions, yeah. I never thought of it as dot math, but it's actually pretty reasonable. Okay, so let's do our substitution here. So we have limit, the dx is still there. We're going to put placeholder limits for now. We'll come back to x later. So, and that should not be a dx, that's going to change to a du. So dx over x is du. So that's that whole part. And then what else goes in the denominator?
U squared, right?
U squared. Natural log of x is going to be u. So that'll be a u squared. And everybody's seen that the dx over x right there, that's becoming du.
Cancel the x's and you left with d.
Ha, 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 ha. Then we integrate. So this is u to the negative 2. Add 1, we get u to the negative 1 divided by negative 1. So negative 1 over u. Placeholder limits. And then we're going to replace u with what it's equal to. So we get negative 1 over natural log of x. This limit is as b goes to infinity. We still have this evaluated from 1 to b. 2 to b. 2 to b. Yeah. 2 to b. 2 to b. Okay. So then we plug in our two values. We have -1 over natural log of b. Minus a minus is plus 1 over natural log of 2. And what does that limit go to? 1 over ln2, yes. This is a positive real number, so this implies, and you don't have to write it, but if you want to be complete, you can say this is a positive real, therefore both converge. And by both, we mean the improper integral and the infinite series. Both are going to converge. Isn't there a way to show just this? Oh, there we go.
Would you say this unit is the most important unit to talk to?
It's important because you use it again when you get into differential equations. And depending on which way you go, you will use series a lot or not so much, depending on which way you go.
Because I saw someone saying it's going to be really important in physics.
When you get to Fourier series, it's super important.
Okay.
Super
What's
important.
a Fourier series?
So we're dealing with random series right now, series of numbers. Next chapter, we're going to do series of powers of x, so infinite polynomials, x plus x squared plus x cubed plus x to the fourth, kind of like a geometric series. So powers of x, infinite polynomial, and it's going to turn out that you can take any differentiable function, sine x, cosine x, tangent x, and you can write it as an infinite polynomial. That's important because polynomials are very easy to take derivatives of and integrals of. You can program that really easily, and you can program your calculator. Then when you get into engineering, you want to write these functions not as infinite polynomials, but as an infinite sum of sines and cosines. And that's what a Fourier series is. You write these functions, infinite collection, infinite sum of sines and cosines with variable periods.
So which method of quote-unquote approximation does our calculator use? Would it use a Taylor series or?
Yeah.
Or
It uses
Fourier.
Taylor's. Yeah, it uses Taylor series. Yep. Okay, let's do another one. So, let's see. Is that all right? So let's just make note in our head. If we had k ln k, we had divergence. We already did that before. But if we bump it up and make it k ln k quantity squared, now the denominator goes to infinity fast enough that the fractions go to 0 fast enough that we get finite. So it converges. So then what they're going to do is toy with us. Down here, instead of ln k quantity squared, they're going to toss in this thing. So instead of ln k here, they're going to slow down the denominator a little bit. It's still going to be going to infinity faster than just k ln k, but it's going to be going to infinity slower than k ln k quantity squared. So they're slowing it down a little bit, and the question is, what's going to happen? Is it going to converge or diverge? We'll get to that in a moment. All right, so let's do this one. What is your hunch? When you look at 26, do you think it's going to converge or diverge?
Converge.
So it's true that the denominator grows faster than the numerator, so the terms are going to 0. But if you think about the dominance, you have a k squared over a k cubed. K cubed dominates the bottom. So if you simplify k squared over k cubed, you get 1 over k. So the effective nature of this is going to be like 1 over k, so it will diverge.
Oh.
So we're going to take the limit as b goes to infinity. Let's just cut to the chase here. We know we're going to go from 1 to b. We're going to change these to x's. So we've got that. So that is the corresponding improper integral. What technique of integration?
Yeah. No.
Faster way.
Log form.
Natural log form. So if we multiply top and bottom by 3, now it's in log form. Now the derivative of the denominator is the numerator. So it is in log form. So this will be limit 1/3 natural log. Absolute value. We don't need absolute value because everything's positive here. This is going to go 1 to b. Bless you. Now we're going to break apart our limits of integration. We'll have 1/3 limit, plug in the b, and we're going to have ln of b cubed plus 5 minus natural log of 6.
It's infinity minus a constant.
So infinity minus a constant is infinity. So therefore this diverges. Daniel?
Okay, do we also assume we don't use absolute value because the integral test is automatically assuming the quadrilateral?
Yeah, that's why I said everything's positive, so we don't need to have the absolute value.
Okay.
If you put the absolute value, it's totally fine.
Okay.
But on this interval, everything is positive. All right, now we get to see with our little ratcheting up. Well, I guess we're ratcheting this denominator down from the last example with the logs. Oh boy. So this is going to correspond to the integral from 3 to infinity. So we're going to do, we kind of can cut to the chase here. And we know that that's going to be limit
Is this one going to be a lot of work?
as b goes to infinity. No,
Oh.
it's surprisingly not. Okay, dx divided by, and once again, what technique of integration do you think we're going to use?
Substitution.
Substitution. What do you think we should let u equal?
Wait, are we using x's or k's?
Oh my gosh.
Oh, that's a good point.
Egad. Unbelievable.
He's using Mr. Voss's method.
Unbelievable. Mixing methods. Good eye. Okay, so what are you going to let u equal? That's what I want to know.
I will go ln x.
All right. Because then you have a u and
So we want to let u be the biggest piece that's easily differentiable. This thing looks weird, right? Well, let's see if we should let u be weird. All right, so if we have that, then du is 1 over the inside, so that's 1 over natural log of x, right? The inside of this outer log, think of it like that. So it's 1 over the inside multiplied by the derivative of the inside,
So
which-
1 over x ln x.
1 over x ln x.
That's nice, actually.
Doesn't that match? Perfect.
Oh, interesting.
That matches perfectly. So we're going to get limit. We're going to convert and have some placeholders for a moment in time. dx over x ln x, all of that is du. So doesn't this just simplify to du over u? That part there is u.
It's GU.
This dx over x ln x. And what's the integral of that?
ln u.
Yeah. ln u. Again, we don't have to deal with absolute values. Everything's positive. So we're there. Then we back substitute, so we get ln of ln of ln of u
What?
of x, thank you. And now we can go back to our x limits. We go back to our x limits. So intriguing.
That's a nightmare for anyone who has to do those parentheses.
And what do we think? Is it going to converge or diverge? Oh, and I forgot limit. Oh my gosh. Don't forget limit. Don't forget limit.
Bad example.
Don't forget limit. I know. Do as I say.
Like limits are the foundation of calculus. Right?
Limits. So limit of ln of ln of ln of x. Ooh boy.
It's like your CD scratches and it skips.
Right. Your math brain is skipping. ln. And that limit is
Ow.
infinity. So therefore, both diverge. Okay, so that little tricky thing there, not fast enough. That denominator is going to infinity, but not fast enough. So ln of k quantity squared, that seems to be kind of our...
What's the threshold?
Well, if we're dealing with this type of thing, it's ln k squared. To try to find something that's going to grow faster than this and slower than the other one with an ln, I'm not sure what it would look like. I mean, maybe you could try ln of k squared.
So how do you write divergence as not part of the set of positive reals then?
Say that again?
So if we can write convergence as something is a part of the set of
Got
positive reals,
you.
are
We
allowed
just
to
write infinity.
Okay.
Just write
So it is.
infinity, yeah. I mean, you can always, anytime you have something that's an element, you can also do things like this. If something is a positive real, you can, negate it like that. So it's not an element. Okay, so that diverges. Don't forget. So let's make sure, every step of the way, let's make sure that we do a census of where we're at. We've now done the two series that we can find S sub n for, geometric and telescoping. We then did divergence test. Now we've done integral test. I think we have 10 total. So we're up to 4. Now we're going to do the next one, which is a P series. P series, 10 total. Pizza series.
Why you call it that?
So here's what a P series looks like. And this should look wicked familiar.
Aw, come on.
Because it's just what we talked about with improper integration. As long as the power, so with a series, instead of an x, you have a k. But it's the same thing as the improper integrals where we had x to the power. And if that power were bigger than 1, we had convergence. And if it was less than 1 or equal to 1, we had divergence. So that's P series. So this is nothing new. This should be old school. The first thing we have to make sure we do is write it in the correct form. When we did improper integration, it meant the x was in the denominator with the power that we could analyze. So same thing here. We need to rewrite this so that the power is in the denominator. So this is going to be k to the what if we push. What is the power on k?
Whoa, no.
So what am I writing? Pi minus e. Right? Push the k to the e downstairs, it becomes k to the negative e in the denominator. All right. So now we have to look at, so this is a P series. So here's how you tell me you know it's a P series. You write P equals and you identify P. Now I know you know it's P series. And is that bigger than 1 or less than 1?
Less.
So if this is about 3.14 minus 2.71. And is that bigger than 1 or less than 1? Less than 1. Therefore, diverge. P series, bigger than 1, converge, just like our improper integration.
What is the P and P series stand?
Power.
And you're also not going to tell us on the test which test to use.
You have to look at the old tests. I usually tell you. Because it can be really time consuming to triage and figure out what test to use. On the exam, I'll tell you. Yeah. Was it?
I have a quick question. Is the reason we combine the K's because they're both K's? Like they
Yes, because they're powers that have the same base. So this power has a base of K, this power has a base of K, so we can combine them.
If it was K to the E plus 1, would we still be able to bring it?
Yes.
Okay.
Yeah, we just have to multiply E plus 1 times negative 1, so we'd have negative E minus 1.
But if it was like C to the E,
But if it's C to the E, we can't combine them. So if we're going to analyze it as a P series, we have to be able to put it in the form 1 over K to the P.
well, in this case, if the numerator was C to the E, we could bring out C to the E out of the sigma, right?
I'm not listening to you. What was that? Yeah, if the C was a constant that was not based on the index, then it would factor out to the front. Is that what you're saying?
Yeah.
Yeah, that's right. You're right. Okay, so write this one on your paper. See if you can figure out what this one does, converge or diverge.
Remember that big flow chart you showed at the very beginning where it's all like we need to be able to do all this in our heads? Can we go back to that to see kind of like where we are?
Was it, is what you're talking about this stuff here? These ones?
Oh.
These are going to be next chapter. So those are next chapter. Here are our convergence tests. So these are the, well, we can count them right now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we'll have 10 total. We'll have 10 total. Yeah, so if you go to handouts under convergence tests, that's where we're chipping away right now.
Gnarly.
All right, is that one going to converge or diverge? Diverge. I hear one of each. This is so exciting. Okay, so the 2 comes out to the front. The 2 doesn't do anything. So the 2 is a constant. And anytime we have a constant, that constant can factor to the front. So what is P equal to? 3 halves.
Bigger than 1.
So 3 halves is bigger than 1, so therefore converge. What did you write P as originally? 2/3, yeah. Yeah, so when it goes down into the denominator, it just changes the sign. You don't have to flip the fraction.
You think you'd reverse chain that right there? I get that done. Wait, would that be 27? No, I'm not even thinking that right now.
Okay, so let's look at this cubed root one.
I'm not doing that.
What is the cubed root of 27?
3.
3, so that could come out as a 1/3.
1/3's K to the 3.
So then down here, we're going to have K to the 2/3 power. Oh, this one has 2/3 power. So this one diverges. So you tell me that you know it's a P series by writing P equals whatever it's equal to. And then you compare it to 1 so I know what you're doing. It's less than 1, therefore diverge. Yep. Beauty. So P series are kind of a, cousin of improper integration. Hopefully these will be easier than some of the other ones.
To get full credit, we gotta show this part. Because like right off the bat, I can see that this one converges, this one diverges, so we have to show this work.
No, as long as you can show P.
As long as I show you.
Yeah,
Okay.
yeah.
So I could just like.
You could get to that, yes. Yep. You could definitely shortcut it a little bit. Okay, so there is a P series. So this just says pick your test. So this is going to give us a little practice at trying to decide what test to use. What do you think for 50?
First, we should always do divergence, right?
And what is the limit of a sub k? Limit of a sub k? What are you saying, Caitlin? Limit is 1, right? The limit of a sub k, so the limit, so we have that. And let's do this like so anally. So this, if you want, remember the limit has superpowers, so it can move through continuous functions. So the square root, so we're so uptight, we want to like do every single detail, then this is what we would do. Because a lot of times we just cut to the chase. So we push the limit through that continuous function, and then this rational function is continuous. So this is really what you're doing when you're pushing that limit inside. So that is what we're doing. Even though we usually don't even write down these steps, and you don't have to. Right? This limit is 1. Let's keep doing. Let's write all the steps just because we're so into it. So the limit of this is infinity over infinity. I don't even want to write that though. So if we're going to get infinity over infinity, we're going to go back to here and use L'Hopital's rule, or you can divide by the highest power of k. Whatever your technique is, you're going to get the limit of 1, which is 1.
It's like, how many steps can we possibly take before we get to the answer?
I know. You can write a lot of steps.
And you can just go completely out of the way and differentiate stuff and then integrate it again.
And this is not equal to 0, so our conclusion is divergence. So the divergence test says if the limit is not 0, it must diverge, because this says in the tail of the series, it's like we're adding 1 plus 1 plus 1 plus 1 plus 1 plus 1. And that diverges. Okay. All right, you all try 52. So think about what test you might use. Go through the sequence. It's not geometric. It's not telescoping. Divergence test, what's the limit of a sub k there? 0. So go through the test then.
Would it be an integral test with PFD?
Would it be a what?
Would that be an integral test with PFD?
You can't use P-series yet because that is not a P-series. It's like a P-series, but it's not a P-series because of the 9. So we can't use P-series yet. We're going to learn another test called the comparison test, which will work if we have something that's P-series-like.
So the only 3 that we can use for now are divergence, integral, and
You
P-series.
can use the integral test. Yes.
I'll use the integral test.
The integral test.
Which
No,
test
it's
is the
not
hardest?
so.
Which test is the hardest?
What about it makes us know we need to use the integral test?
So it's not geometric or telescoping. Geometric has the form a r to the k.
Okay.
So a geometric series has the power up, it's r to the k. It's in the it's the power. The variable is in the power. The index is in the power. So it's not that. It's not a p-series because of the plus 9.
Okay,
If it was just k squared down there, it would be a p-series.
okay.
Divergence test is inconclusive because the limit is 0. So the only thing left is integral test.
And you said not telescoping because?
It's not telescoping because we don't have the plus minus, plus minus, plus minus.
Oh, okay.
Telescoping is usually like 1 over k minus 1 over k plus 1.
Oh, yeah, that's what I meant. Okay.
So, integral test. Right. Integrate. And our hunch, our intuition should be that it converges because it's going to act a lot like 1 over x squared if you look at the integral.
The terms get smaller and smaller.
Which means nothing except that it might converge. So we're going to take the limit as b goes to infinity. So we've got that. And what does that integrate to? Inverse tangent. So we're going to pull out a 10, we're going to pull out a 9. Oops, and we still have limit. So if we pull out a 10 and a 9, let's see, pulling out that 9 is going to give us x divided by 3 quantity squared plus 1. So that is in the form of arctan. We're going to have 10/9 multiplied by limit. That's going to be arctan of x over 3. Reverse chain rule says to do what? What's the derivative of x over 3? 1/3, divide by 1/3, multiply by 3. We have that, from 0 to b. So now we're at 10/3 limit as b goes to infinity. Arctan of b over 3 minus arctan of 0. What's arctan of 0?
0.
So arctangent of 0 is the angle on the right side of the unit circle that has a tangent value of 0, which is 0 radians. So that's going to 0. And what about arctan of b over 3 as b goes to infinity? What's that going to be? Pi over 2. So we will end up with
5/3 pi.
5/3 pi. Now we have to remember our conclusion. This is a positive real. Therefore, both converge. So both the improper integral and the infinite series, they both converge. Any issues? Any issues? All right, what do you think we're going to do on the next one?
Is that partial fraction?
Yes. All right, so do your partial fraction decomp. PFD. So do your PFD, turn it into something that is integrable. Divergence test is inconclusive, the limit 0. we've already seen that these tend to turn into telescoping series. So go ahead and do your PFD. Do your PFD, and then we'll integrate. Actually, we won't integrate. We'll just do the limit of S sub n. No integration. We integrate when we're doing the integral test.
So we can actually find the answer to this one?
Yeah. We're not, we're gonna, we'll use a series technique. We don't have to go to integration now. Was misthinking. No integration. All right, now do your S sub n. Yeah, once you do your PFD, then go for your S sub n and figure out whether it converges or diverges. Anyone having trouble with PFD? All right, let's walk through it then. So with PFD, we're trying to rewrite this expression as two fractions. So it's going to be A over the first factor plus B over the second one. Multiply by the denominator on the left.
So in this case, we don't need to change K to X?
No, not here.
Oh,
Because we're never taking a derivative.
got it.
We're not differentiating or integrating.
Okay.
Technically, we never do, right? Because we can do a DK.
Yeah, we can do DK.
Although
You
it
could do
looks
that.
messy.
So these are both linear, so we can use the convenient value method. What are the two convenient values? -4/3. And what's the other one? -1/3. So if we plug in our convenient value here, we get 0. And over here, when we plug in -4/3, we get -3b. So b is -1/3. If we plug in -1/3, we get 3a. So there are the two numerators, a third and -1/3.
Oh, minus the K, that makes sense.
So when we rewrite it, we will have, so 1/3 over 3k plus 1. And then minus 1/3 over 3k plus 4. And k in this case goes 1 to infinity. Okay. So let's go ahead and factor out the one. Let's factor out the 1/3. And let's just do that right here. So I'm just going to erase this, and we are going to pull the 1/3 out to the front.
So that's going to be 1/3 S of n? At that
Yeah,
point?
exactly.
Ugh.
So it'll just be a little neater if we make these both 1s. A little bit neater. So we have that. Yeah.
Why aren't we doing it integral?
You could do an integral. The biggest issue there is you're going to get, you're probably going to, so let me just think. So if we do,
You get infinity minus.
we're going to get an indeterminate form. If we do the, first off with telescoping, we get to figure out exactly what S of n is equal to, which tells us what S is. So that's going to give us more precision already. Second most, when we start to integrate here, if we integrate both of these are both going to give us infinity. Right? They're both acting like 1 over x. So we'll have an indeterminate form of infinity minus infinity, which is indeterminate. All right, so S sub n is equal to, and when I say S sub n, we're just focusing, we're forgetting about this third for now. So we're just going to sort of ignore the 1/3 for now. Right? The third is not going to change whether we have convergence or divergence. Multiplying by a constant doesn't do anything. Changes the value, but not converge or diverge. So S sub n is the sum of the first n terms. When k is 1, we have a 4th minus a 7th. And I feel like I might want to give myself more space. I think I'm going to do this down here. These things can be kind of long. Okay, so that is our first term. That's when k is equal to 1. Now luckily this index starts at 1, so we know it's just going to end in n. When k is 2, we get 1/7 minus 1 over 10. When k is 3, we get 1 over 10 minus 1 over 3 times 3 is 9, so 13. Plus, then we do some dots in the middle. And then we have to plug in n minus 1. So plugging in n minus 1 there is going to give 1 over 3n minus 2. Minus 1 over 3n plus 1. And then we plug in n, and we get 1 over 3n plus 1 minus 1 over 3n plus 4. So this is when k is 2, this is when k is 3, this is when k is n minus 1, and this is when k is n. All right, so those are the sums, the S of n, sum of the first n terms. Anyone have a question up to that point? Cancellation, fairly obvious. The cancellation is very sequential all the way through like dominoes.
It's pretty.
Very pretty. And then going back the other direction, same idea. First part with second part, first part with second part. So the only terms that are not disappearing are the 1/4 and the minus 1 over 3n plus 4. So there is S of n. And then we're going to take the limit of S of n. And what do we get?
1/4.
So that is the sum of the series.
Except for the fact that we have a 1/3.
So the limit of S of n is 1/4. And so the total sum will be 3 multiplied by 1/4, which will be 3/4.
Wait a second, but it was 1/3.
I don't know. Was it?
Yeah.
It was 1/3.
1/3. I don't like 1/12 though. Total sum.
What's wrong with them?
Thank you, Harrison.
Why does 1/12 keep showing up?
Especially in sums.
1/12 seems like it's showing up an inordinate number of times.
Aren't these problems you play?
Yeah, I know. I randomly sampled things.
Math
Need
is
to
laughing
just
at you.
change those.
Math is laughing at you.
We get people that are like dogs with the 1/12 thing.
And then they just, oh, that's me. You're conditioning us.
Right.
How dare you?
I know. Question, Daniel?
I'm just trying to follow along.
That's all. Which part are you finding these terms?
Yeah, I'm trying to justify k equals n minus 1 and k equals n. I'm just gonna
Because
follow
S of n means the sum of the first n terms. So because this starts at 1, the nth term, like the third term is when k is 3, the fourth term is when k is 4, the nth term is when k is n. So the term before the nth term, the n minus first term, would be when k is n minus 1.
And this is the telescoping.
Telescoping.
And so then when we do telescoping, we have to include k equals 1 to k equals 3, and then we got to leave the dot dot dot.
In the-
k n minus 1 to the k.
Yes.
And that's how the slashes.
Yep. And so then when we do our cancellation going left to right, this cancels with this cancels with this cancels with something in the muck. And then we go right to left, this first one cancels with the second one, this first one cancels with the second one that's right before it
Okay.
that we didn't write. So in the middle, it's like the telescoping piece. It's all collapsing.
Okay.
And the only two terms that are not disappearing are this one and that one.
Very first and very last.
Very first and very last.
Okay.
And then we take the limit, and we have convergence. That's our total sum.
Because 1 over infinity is
0.
so that's why you only have 1/4.
Yep, this goes to 0 here. This part
Yep.
goes to 0.
And we just left the 1/3. We left the constant out. So the constant could have been something like stupid number. Just leave it
Mhm.
as that. Okay.
Correct. Toads.
Okay.
Toads. All right, let's talk a smidge about some estimations. We're not going to do a lot of this, but a little bit. So if we have a series that converges, you can write this equation down. You can write that, it's more intuitive, I think, to write it this way, that the sum of the series is going to be the nth partial sum plus the remainder that's associated with that nth partial sum. So if you've got your series, as you go further and further out, 100 terms, 1,000 terms, you're getting closer and closer to S. So we have a convergent series. It converges to S. That's the sum of the series. And the bigger n is, the closer you are to the sum of the series, and the smaller r sub n is. Right, so S sub 1,000 is going to be pretty close to S, which means R sub 1,000 is pretty close to 0. So the further we go out in the series, the closer we are to S with S sub n, and the smaller the remainder gets. So as n goes to infinity, S sub n goes to S, and R sub n goes to 0.
What's the remainder?
The piece that's between S sub n and S. So if we're adding up all these terms, if we add up the first chunk there, then this part is the remainder. So here is R sub n, here is S sub n. Maybe this is 1,000 terms, we add those up, and then this is the tail. So R sub n is always the tail, and R sub n will be getting closer to 0 if we have a convergent series, and S sub n will be getting closer to S. So you can write this algebraic equation right there. So let's focus for a minute on this inequality right there. R sub n is less than that. So let's again look at this visual thing here. Let's shrink this a little bit so we can see more of it. All right, so once again, if we look at our interval from 1 to n, we can either use rectangles that are shifted to the left. So we're thinking of our numbers as right endpoints, or we can think of our numbers as left endpoints. In both these images, the blue is equal to the blue, the beige is equal to the beige. So the beige is representing the remainder, the blue is representing the S sub n. So this inequality right here, R sub n is in the middle. We're looking over here at the beige. And R sub n, if we integrate the curve, which is red, if we integrate the curve from n to infinity, we can see that the beige is under that red curve. R sub n is less than the integral from n to infinity. Right? The beige is underneath the area. There's all these little triangular pieces that are missing. So R sub n is smaller than that. Now if we do the right endpoint rectangles, then look at this. So now we still have n rectangles, but we've shifted everything to the right. So the first point that doesn't have a rectangle is n plus 1. So we integrate from n plus 1 to infinity. And here the beige is above the red curve. So this, the remainder is, the beige is above the red curve, so the remainder is bigger than that. So the remainder is bigger than this and smaller than that. So the remainder is trapped in between. So now let's come back up here. So when you look right here, there's the sum of our series. it's going to be S sub n. This is going to be an overestimate here. This number, the integral from n to infinity, is bigger than the remainder. So if this is bigger than the remainder, this is an overestimate for the series. And the n plus 1 to infinity is less than the remainder. So if we take S sub n and add the thing that's a little bit smaller than the remainder, we're going to get an underestimate for the series. So that tells us that our series value is in between this upper estimate and this lower estimate. All right?
How are any of these useful if at this point we can't quantify S of n?
Good question. Right now, this is just theoretical. We're just looking at understanding that the series is going to be trapped. The point right here is that we can use an integral to represent a numerical value for the remainder. And so we can get an estimate for the remainder by looking at these two integrals. So it's kind of converting from summation to integral. That's kind of the point right now, is that we can, the important thing is that we can gauge the remainder. And again, in this class, we did it with alternating series, right? Alternating series, we looked at the magnitude of the next term. And we did it in detail there. Here, we're going to just approach it very abstractly. We're not going to go calculate a ton of remainders. When you go into a numerical analysis class, an engineering class, you spend time figuring out, numerically how to find the remainder and how, big you want it to be, or you'll let it be, or whatever.
So
But here, we're doing it more theoretical.
what's important for us to understand out of this right now?
That the remainder is less than that.
Okay. Okay.
All right, so let's just put that. So it's a theoretical concept that if we have a series that converges, you can estimate. You can get an upper estimate if you take your S sub n and add that, and it's underestimate if you take your S sub n and add that. So the remainder is less than that is kind of the main result. Let's take a look. The other possible extra credit question on the exam, Riemann zeta function. So the Riemann zeta function is defined as zeta of x equals that. So zeta of x is 1 over k to the x. Now, that's a very general function. That exponent right there, that x, can be any real number. You can actually even let it be a complex number if you get online. If you look at that Riemann zeta video I have up there. So when x is a real number, the zeta function actually is a p-series. When x is real, right, we're dealing with a p-series. And if p is bigger than 1, you have convergence.
Zeta of -2 is 0?
So this result right here, that 1 over k squared is pi squared over 6, that is an independent result that's called the Basel problem. It was very complicated, so if this problem right here, right there, that one, 1 over k squared, the fact that it is equal to pi squared over 6 is mind-blowing, first off, because you're adding all of these reciprocal squares and you're getting pi. Pi feels very geometric. This does not look like very geometric. Euler in 1734 proved that it's equal to pi squared over 6 when he was 28 years old. And this is a really good video showing how he figured out that.
Is that the 3 blue 1 brown one?
This is true. The 3 blue 1 brown is harder to follow.
With the infinite circle thing?
Yeah,
that's
one's
the only one that makes sense.
That one's a little harder to follow. That video there is very easy to follow. All you need to know how to do is pre-calculus. And that's how he did it. So he proved all these things back when he was a child. When he was 28.
So, so below this, where it says the Basel problem.
Yeah, so we haven't gotten there yet. Hold on.
Okay. Okay.
Okay, so Riemann zeta function, these are special cases. When x is a real number, you get a p-series. So from P series, we know these converge because P is bigger than 1, P is 2, P is 4, P is 6. So we know they converge. Here is the piece that is the extra credit piece. This is the part that is super mind-blowing. Here we have Riemann zeta function, okay, right there. That's an infinite sum. If you look up online, you can show that the Riemann zeta function, the infinite sum form, is equal to this. This is called the Euler product. So this capital P, capital pi, is for product. And you do the same thing that you do for a sum, except that you're multiplying. So all these things are being multiplied together. And the part that's mind-blowing is that you can take an infinite sum, you can turn it into an infinite product, where that infinite product is only over prime numbers. The Riemann zeta function is used in mathematical research to figure out the density of the prime numbers in intervals. So if you look at the interval between 1 million and 10 million, how many primes are there? The Riemann zeta function has a remarkable ability to predict the number of primes in different intervals. And when you look at that function right there, the last thing anyone would think of is a prime number. If you're adding all of these things together, no one's thinking about a prime number. But you can prove that this infinite sum turns into an infinite product where you only consider the primes. And so here is the summation side of it. Here is the product side of it. And if you look on the Google, you will find a proof of that that's understandable with only pre-calculus. And the extra credit question on the exam will either be this or it'll be the Coke Snowflake, one or the other. But you should watch this. That video is really good on how to prove that that's pi squared over 6.
So are we going to have to prove that it's pi squared over 6?
If you want,
on the
no,
test.
on the test. No.
So what are we going to have to do? Find where zeta of x equals 0? Or
No.
Zeta, yeah.
Zeta of, you don't have to do that.
Then what would a problem be then? Just,
From the zeta?
yeah.
Just the extra credit question. That's the only thing we're going to do with zeta function. Zeta function is going to be just extra credit.
So for Coke Snowflake,
Yeah.
that's what would we have to prove for the test?
For the Coke Snowflake, you have to prove that the perimeter is infinite and the area is finite.
Okay.
So if we look at this beautiful table that I spent many hours creating, if you basically just have to, use this, reiterate these three things to get to the perimeter, take the limit, and for the area, reiterate those plus that calculation. And then you'll get infinite perimeter, finite area. And for the Riemann zeta, you want to show that the infinite series is equal to the infinite product.
How do we do that?
That is that. You're going to look on the Google, and you'll be shocked at how easy it is.
So we're going to teach ourselves?
Yeah.
Hell yeah.
Yeah. There's times where you got to teach yourself stuff.
Flashcards are best for that.
See, Thursday? Flashcards are very good for that.
Yeah.
Flashcards are amazing for that. Let me hit pause. All right, who has questions?